Welcome, everybody, once more to the official IAU G2 online conference series. As usual, this is about massive stars, and today is my real pleasure to introduce our next invited speaker, Griffin Hosseinzadeh. Griffin is presently an assistant professor in the Department of Astronomy and Astrophysics at the University of California, San Diego. He got his PhD from the University of California, Santa Barbara in 2018, and the title of his thesis was Proving Late-Stage Stellar Evolution Through Robotic Follow-up of nearby Supernova. And after that, he moved as a postdoc to the University of Arizona's Stewart Observatory at and the Center of Astrophysics at Harvard and Smithsonian. Yeah, in his research, he tried to link the zoo of explosion we observe in the night sky to the stars that produce them, in order to understand the last years to months of stars' life. And he's also interested in studying the remnants of this explosion, like the neutron stars and black holes, through optical observation of gravitational wave sources. His work often use the methods of data science to enable rapid follow-up or last samples of transients. And in particular, Griffin will be showing us how to constrain mass loss processes occurring at later stages of stellar evolution through rapid supernova spectroscopy today. So thank you very much, Griffin, for accepting the invitation of the organizing committee of the IAU G2 Commission. Whenever you want, the floor is yours.
Yeah, thank you very much for having me. Let me share my screen here. Everybody can see that okay?
Yes.
Yeah, thanks again for having me. And I realize this is late for people in Europe, so thanks for joining if you're online. And please excuse, I'm recovering from a cold, so my voice is very nasally today, but hopefully it will last throughout the talk. So what I want to talk about today is probably different than what you've been hearing in the Massive Stars seminar series, but very related, I think. I want to talk about how we can use observations of supernovae to understand their massive star progenitors. So the way I like to introduce this topic is with this video. Maybe some of you have seen it before. This is a artist rendition of what it looks like to watch a supernova if you were really up close. And the point I want to make is, look, this goes from something that looks like a star to something that looks like a supernova in a matter of just a few minutes, if you look at this light curve in the bottom right here. And we don't see that star. We can only see the supernova. What we want to do is link our observations of the supernova back to the star that was there before to understand what the star was doing, what its environment was like before explosion. And so to do that, we have to get very early observations of that supernova. So in other words, transients teach us about stars, and that's why transients are interesting. Very, very rarely, almost never, can we actually observe the star during its normal lifetime and watch it explode. So we can only do indirect constraints on the star by observing the supernova. But we do that by observing the first hours to days after explosion, when the supernova physics is still sensitive to the initial conditions of what the star was doing prior to explosion. And these phases of the star's life that we're probing, the last years or months of the star's life, just from a timescale argument, we basically can never observe these in the Milky Way. So the constraints on what the star is doing at this time are very poor. And supernovae are one of the few ways that we have to actually probe that. So I'm going to have two big sections of the talk today. One will be the science section to talk about how can we use type 2 supernovae to probe mass loss, specifically in red supergiants, but actually it's very broadly applicable, the ideas that I'll present here. And second of all, how are we actually doing this in practice? Many of you are aware that LSST started 2 days ago. And so it's a very exciting time to be in transient observations, but things have to change about the way that we're conducting our follow-up campaigns. And I'll talk a little bit about what that looks like now. But first, let me start with red supergiant mass loss. So here is a picture of Betelgeuse. And the main point that I want to bring up with this picture is you notice this is not just an isolated star in a completely clean environment. There's circumstellar material at all different radii, at different densities, and we would like to understand how that gets there. The idea that you just have a spherical supernova exploding into empty space is completely wrong. We already know that, but we still kind of make that assumption when we do a lot of our modeling work. So specifically, a type 2 supernova just means that it's hydrogen rich. And so that means it is a hydrogen-rich star. It still has a large hydrogen envelope. So these come from red supergiants. And by observing these type 2 supernovae, we can get probes of red supergiants in much greater numbers than we can in our galaxy and its satellites, because we have the whole sample of red supergiants out to very distant galaxies to deal with. And we can observe the latest stages of evolution, the last years and months of its life. So the question is, what would it actually look like if you have a red supergiant like this exploding into a very complicated circumstellar environment with lots of material? From a supernova perspective, it looks like this, where you have, a hot thermal continuum. It's because of the expanding photosphere. The temperatures are very high, tens of thousands of kelvins. But on top of that, you have these narrow emission lines, which come from photoionized or shock-heated material in the environment around the star. So when we see a spectrum like this, what it means is that there actually is dense circumstellar material very close in, confined around the star. And if you notice, that disappears after just a few days. If you compare the red spectrum taken at less than 1 day after explosion to the purple spectrum, which was taken 6 days after explosion, you realize that these features are only visible for a few days. And that gives you a constraint on how far out the CSM goes, because the supernova is expanding and overrunning all of this circumstellar material. And once that's over, you can no longer see those lines. So you get a constraint on the density profile, which looks like this, where there's some dense CSM very nearby the star, and then that falls off quickly. And potentially there's some underlying more extended material there, but that is not visible to the spectrum in the same way. Another piece of evidence we have for this is actually from the light curves themselves. So even without spectra, you can see evidence of this, in the sense that this is some modeling work by Victoria Morozova, that if you model type 2 supernova light curves with no circumstellar material, or it's written here as a wind, debatable whether that's the right word or not, but you get a much slower rise. That's the dotted lines here. And this is especially true in the bluest bands towards the bottom of the figure. Whereas what we actually see is a very fast rise that comes to kind of a peak and then declines onto its plateau, which comes from the hydrogen recombination. And so by fitting the light curves, multiband high cadence light curves like we have here, with models of explosions into a circumstellar material, you can get a constraint on the density and extent of that material. And we see that in many cases, maybe even in most cases, the light curve is better explained with the presence of circumstellar material than without it. Okay, lastly, in very few cases, although this is going to change soon, we actually see direct evidence of activity in the progenitor star prior to explosion. So this means that what you're seeing here is a light curve of a type 2 supernova 2020 TLF. To the right-hand side of the plot, after zero here, or after, I guess, is with respect to maximum. So the part that really shoots up quickly, that is the supernova, right? But prior to that, the red and yellow points, there are some detections of, I guess, the progenitor, unclear exactly, but this is at like -11 or -12 absolute magnitude, which is far too bright to be a quiescent red supergiant progenitor. So something is happening here. Unclear what that is. Maybe some kind of pre-explosion eruptions or activity, but whatever, the red supergiant is doing something very interesting at this time, which is probably related to the circumstellar material that we later see. And if you note in this figure, this one was detected because it was very nearby to us. But once we have LSST going routinely detecting these type of things, we should be able to see this activity, if it is happening, out to something like 100 megaparsecs. So the numbers that we'll get are much, much higher. Is one of the most exciting things I think that LSST will do for us. So let me start with just an example. Many of you are familiar with this very famous supernova that happened a few years ago, 2023 IXF. This was in the Pinwheel galaxy, shown on the right, at only 7 megaparsecs. So only 1 or 2 core collapse supernovae are this nearby per decade. So this was really a unique opportunity, at least in my academic timescale, to study something so nearby and get a really complete data set of what does it look like to watch a red supergiant explode from the earliest moments of the explosion, hours after explosion, and follow it for a very long time. I want to just mention as an aside that this supernova was actually discovered by an amateur astronomer in Japan, Koichi Itagaki. If you've not heard of him, he's really an amazing character. He has no formal astronomical training, but he basically operates his own robotic observatory. It's not robotic, I guess, but he operates his own observatory in the mountains of Japan, and he searches for supernovae, and he's one of the most prolific discoverers of supernovae, even in this age of giant surveys. There's a profile on him in Science that I highly recommend you read called The Star Watcher, if you haven't heard about him. So he discovered it. Here is the plot of the early light curve. He discovered the supernova with the point labeled I for Itagaki, which is around very near the right-hand side of this plot. But in fact, after he had discovered it, a lot of amateur astronomers realized that they had been looking at this galaxy in the night prior to his discovery. So we actually recovered image of this going back by almost a whole day before discovery. And this was before any professional astronomers had gotten on this target. There are several good things about this. One is that the time of explosion is very well constrained because there were limiting magnitudes from amateur telescopes just a few hours before the first detections that we could see. So we know really when this exploded to within a couple of hours. And more importantly, I think, this is probing a luminosity range fainter than -14 in absolute magnitude that is almost never detected for any transient, just because it's rare to have something so nearby, and so we're limited by the depths of our surveys. And of course, we're limited even for nearby stuff by discovering it early when it is at this faint absolute magnitude. So I'm going to show you some strange stuff that's happening here, but the point is maybe it's not strange because we just never observe this regime. So maybe this is actually common and we don't know. So this black line here, you may be wondering why it doesn't go through any of the points. The reason is that this black line is just a fit to the early light curve starting at about a day after explosion. This is like how you would typically, how as a supernova observer, I would typically estimate what the explosion date was. I would fit a line through the early light curve. It could either be something as simple as a polynomial, or it could be some more physical model trying to explain what the evolution of the early light curve looks like to estimate when the explosion date was. But it turns out that even though we have very densely sampled early light curve using all of our facilities, I'll talk more about those later in the talk. If I fit that curve, it's very inconsistent with the first day from the amateur photometry. Right, so that's telling us that something strange is happening during this first day where there's a slower rise and then suddenly it starts rising faster. Right, and this is not what we expect. If it was just an expanding sphere, we would call it an expanding fireball. It should basically go as t squared with the area, the surface area of this expanding sphere. And that does not seem to be what's happening. At least it's not that simple during the first couple of days. So one thing I worry about is maybe we've been misestimating explosion epochs for all type 2 supernovae for all of history because we haven't been understanding what they're doing during this first day. Now, if I ignore that for the moment and just try to actually fit a model to data later than one day, there actually is a fairly good fit, even with a pretty complex physical model. This is a model of just shock cooling emission, meaning that the supernova is expanding after the shock has run through all of that material and is cooling off as it expands. This does not account for any circumstellar material in this model, and yet the light curve fits pretty well. And from this model, you can estimate what the progenitor radius was, because the evolution is sensitive to the radius of the progenitor star. And we get something that is pretty reasonable for a red supergiant, 400 solar radii. But again, even this model is not at all consistent with the first day of observations. So the question is, what's going on during this time? In our paper, we talked about a few options, but of course, I'm open to any other creative ideas that people have about what's happening during this time. So if it is, one piece of the question is, when did the actual core collapse happen in this timeline? It could be that the core collapse is at what we're calling day one, and that there was something happening with the progenitor before core collapse. So in other words, that first day of observations was really some extreme eruption right before the explosion. But at least I'm not aware of any models that would predict such an extreme eruption on the 1 day before explosion timescale. It could be that this 1 day is the time between the core collapse and the shock breaking out of the stellar envelope. It does, red supergiants have a big envelope, so it does take some time for the shock to propagate out through that envelope. It could be like a day long. But then it's unclear why we would be seeing light from that if the shock hasn't broken out yet. There's some hints in the literature that something like this could happen, especially if the explosion is not spherical, or there's some extreme asymmetry, that you could get shock emission leaking out before the actual shock, or at least from some part of the star before it breaks out of the entire star. I would say this is very speculative, but something we have to think about just because we're out of good ideas. I think that probably the most promising thing is that, yes, none of our crazy speculation is needed. You have the shock broke out at what I was calling day zero there, but then something strange about the distribution of circumstellar material is slowing down the diffusion time, or actually slowing down the ejecta as it is plowing through the circumstellar material. And so that little extra emission is coming basically from circumstellar interaction. But we don't have a really convincing model showing that this could happen, that this actually matches the emission that we see. The closest we get is some work by Daichi Hiramatsu, one of my collaborators, who has modeled for this specific supernova, in fact, what would the light curve look like with different, a grid of CSM parameters. And you can see on the left-hand side that he gets some models that match the main light curve starting after 1 day. And if you look on the right-hand side, you see there are also some models that match that initial excess emission during the first day, but those are not the same models as each other. So this is telling me, okay, there's something here, I think. This may be the answer, but his assumption of like a continuous wind is not correct to explain this. So it could be that, the wind, the mass loss rate changed at some point very late in the evolution of the star. And so you have kind of a 2-component CSM or something like that, some kind of variable mass loss rate. And maybe you could get something like this. But at least I haven't yet seen a paper showing me a model that actually matches this light curve. So I think there's some work to do there. Now, so far, I've just been focusing on the light curve, but in fact, the spectra give us a lot more information. We got an amazing early spectral series here. These are, you can see lines changing over the course of hours. All of these spectra were taken within the first 3 days that you're seeing on this plot. And you see these very high emission lines, carbon 3, nitrogen 3, nitrogen 4. These are coming from the CSM that's been excited by the explosion in one way or another, and emitting at a very, these very high ionization levels. And those are disappearing over a very short time scale, right? So this is telling us that there is CSM very nearby to the supernova that's getting destroyed. Specifically, look at these lines as they change. And by comparing these to models, the models are quite uncertain, but you can get an estimate of the mass loss rate by looking at these, by comparing these observed spectra to model spectra. And we get something like a pre-supernova mass loss rate of order 10 to the minus 3, 10 to the minus 2 solar masses per year, which again is too much to be a wind from a red supergiant, but it could be something like, some kind of eruption or binary interaction that's stripping a bunch of material. Unclear what the actual mechanism for this is, but it does seem to be that there's something drastic happening in the last years and months of a star's life. We also were lucky enough, because again, this target was so bright, to get some very high resolution spectra of high resolution early spectra of the supernova. And what we're looking at here are the line profiles of some of those same lines in a lot of detail. We don't have the same cadence here, but we have much higher resolution. And you see that these are clearly not symmetrical lines. They have a very strange profile, and they're systematically blue shifted from the rest wavelength. This is from a paper by Nathan Smith, another one of my collaborators in Arizona, who the picture he is drawing from this is that there's some kind of circumstellar disk where some of the emission is coming from interaction with a more spherical component of wind that's shown in the orange there, and some of it is coming from interaction with the disk. Of course, this depends on what the orientation of the disk is with respect to the observer, but this is how you can get a very asymmetric line profile. There's a lot of details that I'm glossing over here, but I would refer you to his paper on it. He goes into great detail about what he thinks the geometry of the system is. But it's important to think about the fact that if there's a disk here, this tells you something maybe about what the mechanism is for creating all of the circumstellar material. Binaries are something that could create a disk, for example. That doesn't mean it's definitely binaries, but it's clear that this is not some kind of spherically symmetric wind. We at least know that. So I showed you before some evidence of precursor eruptions in the progenitor star from a different supernova, 2020 TLF. So we did a similar search for 2023 IXF. This work was led by my collaborator Yize Dong. And he looked in all of the public surveys, including our own, DLT40, for the past many years, and did not find any significant precursor activity at the level that we saw in 2020 TLF. Definitely below the level that we would see for precursors in interacting supernovae, which is actually quite common to see now. He puts threw some toy models in here and saw, there's a few spurious detections, but probably those are not real because they don't match anything that we would expect from a physical model of mass loss from a star. So it's clear that there is some diversity here. Like this supernova is different than another red supergiant that exploded, even though the supernovae look similar in many ways. But something is different about what the progenitor was doing prior to explosion. One last piece of evidence about the progenitor is actually, in this case, we were lucky enough to have time-resolved observations of the progenitor itself in the decade prior to explosion. This is just because it was in such a nearby galaxy that you could actually resolve the progenitor. And so we have archival imaging that actually shows the progenitor was not quiescent during the last decade of its life. It was, varying. This is a sinusoid that we threw in here to guide the eye. I don't know if it's perfectly sinusoidal, but some kind of pulsation or periodic variability in the progenitor. It's clear that that was happening. There's no evidence for kind of stochastic outbursts. Of course, we don't have perfect time resolution, so we could have missed that. But this is another clue about how that CSM is being produced, right? So if you have a progenitor that is pulsating at these very extreme levels, it's probably losing mass. Some of that mass is getting unbound. We recently had Jared Goldberg visiting UC San Diego, and I talked to him about this at great length. He has a lot of models about red supergiants pulsating and losing mass. Some of that mass even gets unbound. So it looks like maybe that is something that is quite common among red supergiants. And so that has then effects on what you see when they explode as type 2 supernovae. So to summarize this evidence, I would say that the future of constraining red supergiant mass loss is kind of taking this three-pronged approach using supernovae, right? So we can get the light curves, and you can model a large sample of light curves pretty easily. We get light curves almost for free now in this era of giant sky surveys. So this will tell you something about the diversity of CSM configurations around red supergiants and the distribution of CSM around each individual one. We can get spectra on a smaller number of objects. That allows us to probe a little bit the composition by looking at the identities of those lines, the composition of the CSM, and again, the distribution of the CSM by watching those lines fade and seeing how long they last. And lastly, in a smaller number of cases, but it will grow pretty quickly, I'll show you that in a minute, we may be able to directly observe the progenitor. Well, either directly observe the progenitor and look for variability, or watch for stochastic eruptions at the point of a supernova prior to explosion. And that is helping us understand what the mechanism is for producing all of the circumstellar material. We know it's there. I think that much is clear now after a decade of this type of work, but we don't really know how it gets there. And that's what we'd like to understand. Okay, let me take a sip of my tea now to fix my voice. And we'll move on to the second section of this talk, which is what are we actually doing now as supernova observers to collect the next generation of data sets like this. Instead of doing, writing single object papers, how can we get a real sample and understand what the population of red supergiants is doing? So I mentioned this at the beginning of the talk. We're all very excited that LSST is starting at Vera Rubin Observatory in Chile. This is going to provide a huge increase in the number of transients discovered every year. Just for some context, let me show you what that picture looks like right now in as of the end of last year. We're actually, people don't realize this, I think, we were already in this regime where we were getting very good at discovering supernovae. I label these as supernovae. I guess we don't know for sure that all of them are supernovae, but probably most of them are. But so our discovery capacity increased a lot in the past decade. This is thanks to surveys like PTF, ZTF, PanSTARRS, etc., Atlas. But our capacity to actually get spectra of them, it has increased, but not in step with the rate of discoveries. So this has led to, in the past decade, we get something like only 10% of the transients that we discover are actually classified, meaning we got at least one spectrum, which, by the way, is not enough for analysis anyway. So we've already been living in this regime of having a massive number of transients and only studying a few of them in depth. And let me show you what's going to happen once LSST fully starts and runs for a long time. This picture is going to change very drastically, right? So the number of discovery, we're now talking about order millions of supernovae per year, at least a couple of orders of magnitude higher than it was in the past. And that will just dwarf everything we've ever done if we can take advantage of those discoveries. And let me just say that, this actually happened already. I stayed up quite late a couple of nights ago to look at the first LSST alerts. These came out on Tuesday night. You can go to any of the big transient brokers. We're using Antares recently, which is developed out of NORA Lab in Arizona. And there's a huge list. We think as of last night, there are hundreds of thousands of transients discovered by LSST after just 2 nights of observations. Let that sink in for a second. Hundreds of thousands of transients, which is the same number that have been reported to the TNS in all of the rest of human history. That's really quite drastic change. We're still learning how to deal with these alerts. But in the meantime, we looked through some of the early ones and found clear examples of supernovae. Here's one, which is, I believe, the first supernova reported from the public Rubin alert stream to the transient name server. This was just thanks to me and my collaboration clicking through some of the alerts and finding things that looked like supernovae and reporting them. And if you go to the transient name server now, you'll see that there's already, at this point, dozens of supernovae that have been reported. As far as I know, this could have changed between the time I went to sleep last night and the time I'm giving this talk. There have not been any classifications yet, so we don't have any spectra, I think, of new alerts, but I bet that will change either today or tomorrow. In fact, we're trying very hard to make that change. But my point is, this is already happening. So be ready for a huge increase in the number of supernovae that we're going to have available to us. But I actually want to make, despite all of my excitement about LSST, I want to make a contrasting point, which is that what we actually want is not 1 million supernovae necessarily. What we kind of want is quality over quantity, right? We learn a lot from these individual supernovae that we get really rich data sets on, where we can get time-resolved spectroscopy over the first few days, where we can get all the wavelengths, including out to X-rays and even gamma rays, where we can get observations when it's still very faint, right? And so what this picture is showing you here is a few different science cases in the colored bands that are things that we care about. Shock cooling is what I was talking about earlier. The very early stages of core collapse supernova are in yellow there. Precursor outbursts, meaning that whatever we think might have been producing the CSM, in orange. A couple of other science cases that you may or may not care about there, other types of transients. What apparent magnitude those go to versus distance. And so we just drew a line here at 40 megaparsecs where we can see all of this stuff if we discover it early enough. And this plot is essentially the inspiration for the DLT40 survey, which I'm a part of. This has been running for a long time now and discovering lots of young supernovae. It's only discovers something like 10 supernovae per year, because that's all there is out to these distances. But every single one of those is discovered within a day of explosion, because we just survey nearby galaxies every single night. And so we will almost always, unless there's a technical problem or bad weather or something, we'll almost always have a constraint the previous night showing that it had not exploded yet. And so each one of these 10 supernovae will get a data set like I showed you there, a massive amount of follow-up, and it's probing this fairly unexplored parameter space of the very low luminosities. What is the supernova doing during its first day of evolution? And you can do all of this, with only a limiting magnitude of 19. So you can use 40-centimeter telescopes to run a survey like this. You don't need Keck, you don't need LSST to do stuff like this. So as I said, DLT40 has been running for a long time, but actually this is nothing new now. Lots of surveys discover young supernovae. And so what we're leaning more towards is, we're still running our survey, that's not going to stop. But the most powerful constraints actually come from combining data from multiple surveys, where we may have a discovery of a supernova at our small telescope in Chile, but there was a non-detection previously from Atlas in South Africa or something like that. So you can get much tighter constraints by combining all of the public photometry across all of these surveys. And so this becomes basically a software infrastructure problem, where you have to aggregate all of the photometry across all the different surveys, match against point sources to get rid of variable stars, match against galaxy catalogs to understand if these are truly nearby, get a redshift, etc. And so we have spent a lot of time building the infrastructure to do this. Right now, we're using our target and observation manager, which was actually originally designed for a gravitational wave follow-up project, but it turns out a lot of the tools are broadly useful. You can see my paper from 2024 for a lot of details on how this works. I won't go into all the infrastructure here. because a lot of people get bored by that kind of thing, even though I think it's very exciting. But the summary is we're trying to aggregate all the photometry from all public surveys and just get an alert for ourselves on Slack anytime there is a nearby supernova that needs rapid follow-up. So we want to make this routine where we discover nearby supernovae very early and get spectra as soon as possible. And in fact, we're going even a step further than that, which is that you can combine data from multiple surveys where one is very deep, and you can get good limits from a deep survey, but one is very high cadence, so you can get good time resolution from that. And you use the power of both of those to discover supernovae at these early times, but out to much greater distances than we've been able to in the past. Right? So expanding our horizon from 40 megaparsecs to 50 to even 100. Right? And so the way we're trying to do that is with one of our large Noir Lab survey programs, where we're going to shadow the LSST footprint with the dark energy camera on the Blanco telescope in Chile. The PI of this is my collaborator, Dave Sand in Arizona. So we have a 3-year program now where we have time on the dark energy camera, which is not as deep as LSST, but is still quite deep compared to your typical telescope. And it will observe the fields. LSST is very deep, but doesn't have the time resolution to discover young supernovae very often. But we can make up for that by shadowing the field with DECCAM the night after and the night after that. So filling in the cadence with our own program and using LSST for what its strength is, which is depth. And by doing this, if you have a non-detection in LSST and you have a detection in DECCAM the next day, then you know that that is a young supernova that exploded within the last 24 hours. So we think that this will find something like 25 supernovae. The idea is to target nearby galaxy clusters like the Virgo cluster and a few other more distant ones. And we will immediately release all of these discoveries as soon as we find them to the transient name server, so that, of course, we will follow them up ourselves, but so can anybody else. So this should increase the number quite a bit, and I think is one of the best uses of LSST in terms of young supernova science. Okay, so of course, the goal is not just to discover them. The goal is to actually gather complete data sets. As I showed in 2023 IXF, this is something that has been rare. As I said, that only comes around once or twice a decade that we can get a data set like that. But we'd like to change that and make this possible for a larger volume of supernovae. So we also have a coordinated spectroscopy follow-up program where we're going to target supernovae in host within 50 megaparsecs, most of which will also be targeted by the previous program I described with DECCAM. If we're sure that they've been discovered within 2 days of explosion, we're going to try to get the full optical to near infrared spectroscopic range every day for the first 3 days. And we'll really be able to see those flash features evolve over short timescales. Then we'll continue to follow it normally. That early time is marked in purple in this plot. For a few random supernovae, you may want to focus on 23 IXF in black there. 2016 BKV in red, which is a lower luminosity type 2 supernova. We can get observations still when they're very faint, which has not been possible before, and then do more routine spectroscopic follow-up around peak, and then continue to follow them to late times too, which is another regime that hasn't been probed as well. 100, 200, 300, a couple of years after explosion, as far as we can go with the telescopes that we have. So to do this, we're coordinating a lot of different facilities. We have a 3-year survey program on SOAR, which is a 4-meter in Chile, very nicely located with respect to LSST so that we can get spectroscopy right away. We also have a 3-year long-term program on Gemini to get rapid spectroscopy in the same way. Gemini is also in Chile. And then there's another one in Hawaii a few hours later, if we miss it with the one in Chile. We have Las Cumbres Observatory, which is the spectrographs are located in Hawaii and Australia to get more routine spectroscopy while at peak. And then we want to get deep nebular spectroscopy using, again, SOAR, Gemini, and the big telescopes we have access to through our collaboration CAC, MMT, SALT, etc. And so we are calling this program PASTA, the Public Eon Spectroscopic Survey for Transient Astronomy. It has a lot of constituent programs. Again, I'm the PI of the SOAR component. Las Cumbres Observatory has a key project for supernovae. The PI is Andy Howell. We have our Gemini programs led by Jen Andrews and Dave Sand. We have institutional SOAR time from several people. And we also have a couple of, I haven't had time to go into depth about the new firm program led by Charlie Kilpatrick. That's another component of this. But we're trying to take advantage of this new campaign called EON, the Astronomical Events Observatories Network, where observatories want to work together to follow up time domain events in a coordinated way, rather than all acting independently, getting redundant data, or getting not enough data. And so this is essentially our answer to that call to try to use EON to do spectroscopic follow-up of young supernovae. And so, we have promised in our proposal and in all of our public announcements that we are going to get classification spectra as soon as possible and release them publicly so that other groups can follow them up. Any other data that we collect on SOAR and GMOS, the Gemini optical spectrograph, will be released on WISE-Rep in real time. We're not waiting for the publication. So we're just going to release all of our data publicly, and people can use them as long as they cite our program. I think that's the way to do things these days. If you want some more details on this, you can go to our website. It's very minimal, mostly because I didn't have time to make a good website. But if you want at least the details of what we're doing, go there, and there's some information about it. So, we're building both for this program, both a worldwide observatory network. The point I want to make with this map, you already know where all the observatories are, I think, so I don't need to go into detail here. But the point is, we have surveys, all of the big time domain surveys. Some of, we operate DLT40, but there's also many other ones. And we have spectrographs that can promptly follow those up, usually at the same site. And if not, we have things just to the west of them that can follow them up a few hours later. So the idea is that we should always have some facility available to get spectroscopy of any new event that we discover. And this means, of course, that we're also building a worldwide collaboration of people to work on this. This collaboration is just completely open. The only thing required to join it is that you are actually willing to help us do the work. Otherwise, I don't know what it means to join the collaboration, because our data is already public. So if anybody is interested in young supernova science, I know this maybe is not the right crowd, but maybe you have some friends. You can see our astronote where I announced the campaign, and just email me if you're interested in working on this with us. We're very open to new collaborators that want to work on young supernovae. And of course, I can't fail to mention, especially because many of you are in Europe, that of course our name was inspired by Pesto, who has been running a supernova spectroscopic follow-up program for a decade to great success. And they just ended actually at around the same time that we were starting our program. So congrats to them, and I hope that we can carry on this legacy with a slightly different focus using another 4-meter telescope in Chile. So maybe you can see where this is going. We just want to create what we think of as the ultimate time domain follow-up machine, in the sense that I don't really care which telescopes I need to use. I just want to get young spectra of these young supernovae as often as possible, and collect these kind of golden data sets for a much larger number of supernovae than we've had in the past. And right now, there are humans involved in each step that I described, looking at the alerts that are coming on Slack, reducing the data, reporting the results to TNS or whatever. But we're actually very close to automating a lot of this stuff. So the ultimate time domain follow-up machine, emphasis on machine, would be to just trigger the optimal telescope based on the brightness of the target and the location on the sky, northern and southern hemisphere, automatically reduce the data and send a classification to the TNS. There are groups doing this in ZTF, for example. We're very close to this now. We actually do have automatic data reduction and classification, but just we haven't plugged it into the step where it gets sent to the TNS. A human still has to press a button, but that's very easy. and then kind of just get automatic spectroscopic follow-up immediately following that for days and even months. We kind of know what to do based on what the supernova is. We have to get some information early on and then decide how to respond to that. But we're close to being able to just make this fully automatic. And of course, we would like to add other facilities too. We have a lot of big telescopes in our collaboration already. But if anybody has a telescope that they'd like to plug into this, we're very happy to talk about that. There's something in the chat here. Oh, okay. Thank you, Miriam. Okay, I'm coming to an end here, but I want to just give a quick advertisement for those of you that haven't heard yet. So my department at UC San Diego we're a new astronomy and astrophysics department. Astronomy has been happening at UCSD for many decades, but we started a new department separate from physics only 2 years ago. And so there's a lot of opportunities here if you're thinking about graduate studies, postdoc, et cetera, not only in supernovae, but in lots of stuff related to, basically any field of astronomy, including a lot of stellar astrophysics. So take a look at our website, astro.ucsd.edu, and see what's happening. San Diego is a beautiful place. You can see how sunny it is outside in the middle of February. So please don't hesitate to reach out. And if you're in the area, stop by and visit us. So thanks for listening. If I could give a couple sentence summary of my talk, it would basically be type 2 supernovae are really powerful probes of massive star evolution, especially if you can get observations right after the explosion. And we're building the infrastructure, both software and human infrastructure, to greatly increase the number of young type 2 supernovae that have these golden data sets in the coming few years. And if you're interested in talking more about that or collaborating, just email me. I'm happy to talk to anyone here. So thanks a lot. Happy to take questions.
Thank you very much, Griffin, for this amazing talk. I like it very much. 3 parts of your talk, different topics, but the 3 are very, very interesting, including your publicity of your institution. So this is also
Thank you for encouraging that.
Yeah. Okay. So I have some questions just for my own curiosity, but let's see if the audience can start with any question people may have to Griffin. Reinhold?
Hey, yeah, can you hear me?
Yeah.
Yeah.
Hey, Griffin. Good to see you. I had a question about the model you showed in the first part for the supernova that it had to have a disk around it. And you mentioned this could come from binaries or something else. I'm wondering how extended the models for this disk allow it to be. Is this something that could come from a rapidly rotating progenitor that's kind of shooting out mass sort of on the equator, or would that be not confined enough?
Yeah, that's a good question. I don't know quantitatively the answer to that question off the top of my head. We'd have to go dig into Nathan's paper. My first thought is, so it doesn't need to be a binary, I think, to produce this, but you have to the point is that with these observations, we're only probing whatever like the innermost part of the disk is. So it doesn't tell you about the extent of that disk. It constrains only the density, essentially, of the CSM right there. And so I guess I'm not familiar with how the densities of that kind of rapidly rotating star would compare to what you could get from binary interaction. But that's how I would approach this problem, is by figuring out what that density could be and comparing it to what we get from fitting the spectra. I don't know if you know more about it, actually.
I sort of just said, brainstorming. Thank you.
Mm-hmm.
Any other question? Note I can make one. So I have several. One of them, what are the perspectives to combine the amazing time domain data sets that you are obtaining with direct information about the progenitor? So is there enough data from photometric surveys once you have the supernova, to go back to the images and say, this was a red supergiant, this was a blue supergiant,
Yeah,
or
so I kind of glossed over that, other than maybe this slide, but so the point is that in the past, we've been very limited in being able to directly identify the progenitor to only the very nearest galaxies that had either HST or JWST observations. Just serendipitously, they had observed that galaxy before the supernova exploded, and then you can try to figure out what the actual progenitor star was. And so in all of those cases, it's true that they basically identify a red supergiant progenitor, but there's not too much information you can get. You don't have time resolution or anything like that. So you just see something that's consistent with a red supergiant there. But one of the most exciting things that I kind of didn't mention is that there's the possibility for LSST itself to start directly observing these progenitors in the nearest galaxies. So like we could actually get light curves of red supergiants prior to explosion and then see the explosion all within the same survey.
but
And so then you would really
how you do
know.
that before the explosion? How you know this is the one, or is because you
No,
have
you don't know
monitoring?
prior to explosion, but I'm saying you could get, if you can identify individual stars in nearby galaxies in the LSST data set, you can see probably red supergiants pulsating in there, and then some very small number of them will explode while we're watching. And
So
so
it's a
then you'll
question of
get
the
this whole.
statistic. No, increasing the statistic,
Yeah,
you will have more chances to also have
yeah. The point is just that we haven't really been able to get light curves of red supergiants on this scale before the depth of LSST. So that's what's going to change, is that we'll be able to get potentially for many more nearby galaxies than in the past, get time resolution on what the progenitors were doing before they exploded. But we're still pretty limited to nearby galaxies. That's the point.
Okay, thank you. So before jumping to next question, there is one by Seng, who cannot use the microphone. Is maybe you can read it yourself in the chat?
Yeah, sure. So do some massive stars undergo failed supernovae due to extreme mass loss? And have you ever encountered such a case? Yeah, so this is another big question in our field, which is, do all the red supergiants actually explode as supernovae, or do they sometimes the supernova fails and the material falls back, or even a direct collapse to black hole? I would say there's quite a bit of excitement about this. There's work by Day. There's work by Emma Bezor. There's work from the Ohio State group, the Survey About Nothing, looking for failed explosions. And there are a couple of candidates now. I can't remember, 2 or 3, I think, candidates for failed supernovae. The problem is, in my mind, so it could very well be that what we observe there are failed supernovae, but the models are just not clear enough to tell us if that, and our data set is not complete enough to tell us conclusively what is happening there. There's several other options related to like dust production or stellar mergers or things like that that would look very similar to what the failed supernova light curve is supposed to look like. And just given the data we have, I don't think there's a 100% clear case. It's a little controversial. I think people would disagree with me on that, but certainly people are excited about this and looking for it.
Okay. Any other question? Not, I go for my second one. So, yeah, from the light curves or the light curves that you have transients and blah, 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 but then you have to filter and at some point find the objects that are of interest for you. In your case,
Yeah.
you're talking about supernova related to red supergiants. So you know already from the observation that you've been taking for all these years, what is the percentage of these transients that at the end are targets of interest in this connection with the red supergiants?
Well, okay. Broadly, yes. Like, something like 40–50% of the supernovae we discovered are going to be from red supergiants, something like that, because they're quite common compared to the more massive stars that make up the rest of them. The other half are like type 1a supernovae. So we know kind of what rate to expect. It's still not straightforward always to figure out which one is the how to filter that stream to find red supergiant explosions. I've done some work on that before. There's kind of two different approaches here. One is to try to do some kind of simple filtering where you use contextual information, like what galaxy did it happen in, and maybe how fast is it rising, what color is it, if you have two different filters. And you can make an educated guess about whether this is a core collapse supernova at least, and try to get rapid follow-up of that. The other approach is, if you don't care about the rapid follow-up component, then you can use machine learning to classify huge samples of just light curves after the fact. So I could go back, after LSST has been running for a year, there's going to be something like 2 million supernova light curves in that data set. I won't have gotten spectra of 99.9% of them, but there's still useful information there where you can train your machine learning model on supernovae where we do have a classification and we have a good light curve, and apply that to just the light curves coming from LSST, and you'll get at least a probabilistic classification of which ones are likely to be type 2. And so you would end up, with a sample of order 1 million type 2 light curves with no spectra, which you could still do some science analysis on. You could do, fitting all the light curves and looking for how often is CSM needed, et cetera. Anything you can do without spectra, you could do on that gigantic data set. And that, I think, is a very exciting avenue for work too. It's actually quite contrasting with what I presented here, where we're trying to get really good data sets on a small number. You can also get photometric only data sets on a huge number and do a lot of exciting stuff.
Great. Now we have a question by Tim Parton, and it's also related to something I wanted to ask. So we are going to have statistics more than what we need, but then at some point it's great to have the observation, but we need to connect this to the physical problems that we need to deal, no? And at some point,
Yeah.
I guess that you will start having observations that are just a repetition of things that you've seen before. So once you have, I don't know, hundreds of this type of supernova, it will be enough, or maybe not. So is there a plan to say, okay, we have enough of this, let's concentrate in other type? And connected to that, the question by Tim is, do you think that with LSST, we now have the tools to solve the red supergiant problem? So once there will be enough observation for that, it's not worth it to continue observing, or you think that it still is worth it to continue going for that?
Yeah, it's a big question. I mean, yes, if we ever completely, fully understand all aspects of red supergiants and their explosions, then sure, we'll move on to a different new topic. But I don't really think we're close to that now. They are the most common type of explosion in the universe, but we don't understand. We only understand them at a very basic level. Like, we are now, just in the past 10 years, beginning to understand there's CSM there, but we don't understand how that's produced. We don't understand what the diversity is, because we only have order 10, maybe 20 supernovae with data sets like this ever. And so that is not really enough to span all the axes of variation that there can be in the red supergiant population.
It's because the variability of all these light curves is large enough to say, okay, we need to complement with. Okay.
Exactly. So I think there's work showing that even for two red supergiants that seem to have the same initial mass, there seem to be very different outcomes in terms of the supernova and what CSM is there. And we are just beginning to be able to understand why that would be. So maybe it's related to binary interaction, maybe something about metallicity. I don't know. There's so many options. But I think we're not close to having the data set that we need to answer this on a population level. The red supergiant problem specifically is more related to the masses of the progenitors. And so that is a slightly harder question because it's very hard to get a initial progenitor mass from supernova observations. The only way we've done that in the past is, again, those few cases in nearby galaxies where you happen to have a direct observation of the progenitor. And even then, it's hard because you just get a measurement of the luminosity and you have to connect that back to the mass. So, maybe, but I still think this is not exactly the problem that LSST was designed to solve. So I think that problem can still persist for a long time.
Okay, maybe Tim, you want to add to your question further? No. And we have a question by Kunal. Maybe you can ask yourself, Kunal.
Hi, thanks for the talk. I had a question actually about type 1b supernovae where the progenitors can be much more difficult to find in archival data. Do you think with LSST there is any hope to start seeing any of these, or is it still beyond the reach of what we currently have?
Yeah, that's a good question. I haven't looked into that specifically at like a quantitative level to see how many we would expect to see. In some sense, there's a trade-off here between type 1bcs are going to be rarer, so there's not going to be as many in the same volume where we can see red supergiants. Maybe we will detect some with LSST, but I guess the short answer is I don't know the answer to that question. I'm sure there will be some improvement, but I don't think it will be. Again, this is not what LSST was designed to do specifically, to get direct observations of progenitors. That's really hard to do other than in the nearest galaxies.
Okay, thanks.
Okay, any other question by the audience? Last chance. If not, you can connect with Griffin, or even if you are seeing this talk in YouTube, I'm happy that Griffin will be happy to answer you back.
Yeah, thank you for having me.
Yeah, thank you very much. And see you soon.
Bye, everyone.